Table 8 Note 2 states that the values in the table are valid for a 10 degrees Celsius, equivalent to 18 degrees Fahrenheit temperature change. This means that the table provides data for how different materials will expand or contract when their temperature changes by 10 degrees Celsius or 18 degrees Fahrenheit. Imagine you have a metal rod that is 100 centimeters long at 20 degrees Celsius, which equals 68 degrees Fahrenheit. If you heat the rod to 30 degrees Celsius, which is 86 degrees Fahrenheit, it will expand. From the table, you can see that the coefficient of linear expansion for steel is 0.12 per degree Celsius. This means that for every 1 degree Celsius increase in temperature, the rod will expand by 0.12 centimeters per degree Celsius per centimeter of its original length. For 10 degrees Celsius increase from 30 degrees Celsius minus 20 degrees Celsius, the rod will expand by 10 degrees Celsius times 0.12 centimeters per degree Celsius per centimeter times 100 centimeters, which equals 0.12 centimeters. If you cool the rod to 10 degrees Celsius or 50 degrees Fahrenheit, it will contract. The same principles apply, but this time the temperature change is negative. For a 10 degrees Celsius decrease from 10 degrees Celsius minus 20 degrees Celsius, the rod will contract by 10 degrees Celsius times 0.12 centimeters per degree Celsius per centimeter times 100 centimeters, which equals 0.12 centimeters. Therefore, if you heat the rod to 30 degrees Celsius, it will become 100.12 centimeters long, and if you cool it to 10 degrees Celsius, it will become 99.988 centimeters long, all due to the change in temperature. To reiterate the calculation for expansion or contraction, firstly, identify the material and its coefficient of linear expansion from Table 8 or a similar reference table. Secondly, determine the temperature change, calculating the difference between the final and initial temperatures. Thirdly, multiply the original length of the material by the coefficient of linear expansion and the temperature change. This calculation will give you the amount of expansion or contraction in the same units as the original length. It's important to note that Table 8 and similar tables provide approximate values. The actual expansion or contraction may vary slightly depending on the specific composition and manufacturing process of the material. Also, these calculations assume that the temperature is uniform throughout the material. If there are significant temperature gradients, the expansion or contraction may be non-uniform and the calculations may be less accurate. Furthermore, the coefficient of linear expansion can change slightly with temperature, especially over large temperature ranges. For highly accurate calculations, it may be necessary to use a temperature-dependent coefficient of linear expansion. Understanding thermal expansion and contraction is crucial in many engineering applications, such as designing bridges, buildings, and pipelines. Engineers must account for these effects to prevent stress and failure due to temperature changes. For example, expansion joints are often used in bridges and pipelines to allow for thermal expansion and contraction without causing damage. In electrical engineering, thermal expansion and contraction must be considered when designing electrical connections and components. Changes in temperature can cause connections to loosen or components to fail. Therefore, materials with low coefficients of thermal expansion are often used in critical electrical applications. In summary, Table 8 provides valuable data for understanding how different materials respond to temperature changes. By using the coefficient of linear expansion and the temperature change, you can calculate the amount of expansion or contraction that will occur. This knowledge is essential for engineers and designers in a wide range of applications. Keep in mind that these are simplified calculations and that more complex factors may need to be considered in real-world scenarios.